Good afternoon, everybody, and welcome to the Engineering from Anywhere webinar series. Today, we have a special treat for you. We have Mr. David Ratterman here with us, who will be presenting to us today. And let me take a few minutes to introduce him to you. Mr. David Ratterman is a member of the construction service group at Stites Harbison in Louisville. He is a general construction law expert specializing in fabricated steel industry. Mr. Ratterman has developed a national legal practice and advanced study in the practice of construction law across the country. He has also become an internationally recognized writer, speaker, and expert on a wide variety of legal and engineering topics. He is a pioneer in construction law in the United States. Mr. Ratterman has been lead trial counsel for numerous contractors, design professionals, material suppliers, and construction owners involving complex matters of litigation, arbitration, and construction mediation. He's a formally trained construction arbiter and has advocated in resolution of construction disputes totaling well in excess of $500 million. He was also an advisor to the Federal Emergency Management Agency task forces that investigated the September 11th, 2001 collapse of the World Trade Center towers. Mr. Ratterman is a former president of the University of Kentucky Alumni Association, and he was inducted into the UK College of Engineering Hall of Distinction in 2016. So, Mr. David Ratterman is both an engineer and a lawyer, a great background, great experience, and is a great friend of the college. And so we're thrilled, David, to have you with us today and talk to us about subjects that you're deeply invested in and know a great deal about. The subject is monumentality. So David, happy to have you, and the floor is yours.
Thanks, Dean Buckheit. While I'm trying to get my screen up here, is the screen up okay?
Not yet, David. Oh, good. There it is.
Okay. One correction in the introduction. Mr. Ratterman was my daddy, and I'm David. Good afternoon to everybody in the East. Good morning to everybody in the West. I'm going to share a story with you today about the design, construction, destruction, redesign, and reconstruction of the World Trade Center. My involvement in the story began on September 12, 2001. More on that later. This is a version of the story that I share with engineering and architecture students to give them some practical insight into the profession, usually as part of a professional practice course or a professional responsibility course. I begin when I'm speaking with students by congratulating them on their decision to pursue an engineering education. I tell them that their education will benefit them in ways they can't even imagine, and with that education, they're about to enter one of the world's great professions. At a time in the world's history when physicians were diagnosing patients by poking around in goat entrails, and lawyers were holding inquisitions, and astronomers agreed that the sun revolved around the earth, we engineers of the world had successfully built the pyramids of Egypt, the transportation and aqueduct systems of Rome, a mountaintop metropolis in Peru, and great cathedrals and temples on 4 continents. Engineering forged ahead of other professions because, rightly or wrongly, the greatness of a society has always been judged by the greatness of its monumental structures. And there would be no great monumental structures, either physical structures or virtual structures, without great engineers such as those we educate at the University of Kentucky. We see evidence of what has been called the monumentality gene, at least as early as the story of the Tower of Babel in the book of Genesis, where some long forgotten scribe writes, "Come, let us build ourselves a town and a tower, with its top reaching heaven, let us make a name for ourselves so that we may not be scattered about the whole earth. This is a depiction by a Renaissance era artist of how a structural engineer might design a tower that could reach heaven. Genesis tells us what happened to the tower, but it doesn't say much about what happened to the engineers who tried to build it, which takes us from Babel to Babylon and the Code of Hammurabi. It's unlikely that Hammurabi woke up one morning and said to himself, this would be a good day to write the world's first building code. We wonder what tragic event in that earthquake-prone region of the world caused Hammurabi to enact a penal code essentially aimed at the engineers of his day. There had obviously been a structural failure somewhere in Hammurabi's kingdom. Was there a design error, or had a force been encountered that couldn't have reasonably been anticipated? We'll never know. The great liability of the engineer compared to other professions, said Herbert Hoover, one of the greatest engineers of the first half of the 20th century, is that her or his works are out in the open where all can see them. The engineer simply cannot deny that she or he did it. If his or her works do not work, she or he is damned. That is the phantasmagoria that haunts our nights and dogs our days. But great societies demand monumentality, great monumental structures. And society needs great engineers, such as those we educate at the University of Kentucky, to make those discoveries and to build those structures. Architect Philip Johnson, no stranger to great structures, thought monumentality was a good thing. To me, he said in words that could have been taken from Genesis, the drive for monumentality is as inbred in people as the desire for food. All cultures that can be called cultures have built monuments, that is, buildings of unusual size and expenditure of effort that have aroused pride and enjoyment, as well as utility. But architecture critic Louis Mumford, addressing the application of skyscrapers in the urban environment, was not so sure. Actually, he said, the skyscraper from first to last has been largely an obstacle to intelligent city planning and architectural progress. Its chief use has been to overcrowd the land for private financial advantage at no matter what cost to the municipality. In the early 1960s, David Rockefeller, the father of the World Trade Center, could have also been quoting the scribe from Genesis when he predicted that the World Trade Center will telegraph to the world the economic might and preeminence of New York. However, Ada Louise Huxtable, then architecture critic for the Wall Street Journal, cautioned the Trade Center towers could be the start of a new skyscraper age or the biggest tombstones in the world. In a PBS documentary shortly after the attack, Leslie Robertson, the great engineer who had actually been called upon to design the towers, said simply, I just can't make it go away. So now, with that background, at this point, I asked the students to imagine themselves as a young engineer just out of the University of Kentucky College of Engineering, just hired to work as a junior member of Leslie Robertson's team. It's New York City, and the year is 1958. Excavation for the World Trade Center site, shown in the upper left of this slide, proceeded down through 300 years of fill. The site had been a dumping ground for old New York. The Hudson River on the west and structures on the other three sides had to be held out and up by what was called a concrete bathtub. The World Financial Center at the foreground of this slide was built on the fill from the bathtub. You'll hear more about the bathtub later. These were to be the tallest buildings in the world, and in addition to functioning structurally, they had to make sense commercially. They had to contain enough unobstructed, rentable floor space to pay for themselves. Leslie Robertson's design was radical and innovative. Before the decade of the 1960s, high-rise structures were clad in masonry facades, making them heavy and stiff. Use of narrow windows and a primary structure of exterior steel columns made the World Trade Center towers lighter and capable of achieving greater height and more rentable floor space on the same footprint. Robertson and his team understood that this would make the structures more prone to what we engineers call dynamic responses, primarily wind loading. But existing building codes in the early 1960s were simply insufficient to supply meaningful guidance to inform the design. Robertson and his team had to design something that had never been designed before and for which there was no settled academic guidance. Robertson undertook groundbreaking original research in secret in Colorado at no cost to his client. He developed the then radical premise that wind loading on the structure would actually be greater than the gravity load or the seismic load. He not only researched wind loading, he also conducted original research on something called the perception threshold of humans to horizontal motion. What would it be like for humans to work in a building so light and so tall that it would sway in the wind? This had never been done before. He built a full-size room on a test frame to simulate the movement he predicted in his towers, and he determined from this that humans were not sensitive to distance, but rather were sensitive to acceleration. So he integrated a system of dampers into the tower structure. The World Trade Center towers became the first buildings to utilize structural dampers, which are now commonplace throughout the world. In theory, there was virtually no limit to the height that could be achieved with Robertson's design. Height was limited only by the elevator technology of the day. Application of that technology in 1960 involved use of the largest electric elevator motors in the world. More on that later as well. There were 59 18-inch square columns on each side of the tower's four sides, 236 in all, built from steel plate as much as 8 inches thick. They were shipped in welded, staggered, stepped sections, like the ones shown on the screen, and bolted together on the site. Fabricating those sections had been the crowning achievement of a lifetime of engineering for one of my clients. He built them to last, and they did. They held together in sections when they went up, and they held together in sections when they came down. He died recently in his 90s, and he never quite recovered from seeing his steel sticking up through the rubble. Inside the building, those big columns were interconnected by a system of steel trusses. These become a critical part of the story a little bit later. Robertson never stopped reviewing what he called the unanticipated essence of structural design. In a further innovation, the towers became the world's first commercial buildings to resist collisions by an airplane. Let me repeat that. The towers became the world's first commercial buildings to be designed to resist collision by an airplane, such as occurred at the Empire State Building during World War II, when a bomber low on fuel with no payload became lost in the fog looking for LaGuardia Airport. This slide depicts a plan view of the Empire State Building inside a plan view of one of the Twin Towers. Also shown are the profiles of a B-17 bomber, such as the one that crashed into the Empire State Building, and other representative airliners, a 727, a 747, an Airbus, and the planes that actually crashed into the towers, Boeing 767s. Robertson configured the entire structure between the 106th floor and the 110th floor as an outrigger truss that would allow one side of the building to support the other side if something like an airplane came along and took out all of the supporting columns along one complete side of the building. In the engineering world, we call this instantaneous transfer from compression to tension. I tell non-engineering audiences to think of this as a giant seesaw. I take the engineering diagram and interpose the basic elements of a seesaw on top of it. The system itself, of course, is comprised of a number of intersecting outrigger trusses acting at right angles to one another and serving as seesaws. In its simplest form, a seesaw is designed to resist the forces of gravity pressing down on it. If it is in balance and there are no other forces involved, the seesaw stays in balance. To assure that the seesaw remains in balance, we could place blocks beneath each end, or columns. To stabilize it, the entire system would be in a state of compression at this point. Leslie Robertson went one step further. He placed oversized foundations in the ground, larger than necessary to resist a gravity load, and then he pinned it all together. Here's how Robertson theorized the system would react if something like an airliner came along and knocked out all of the columns on one side of the seesaw. Gravity would continue pressing down over the void where the columns had been removed, but the force on the opposite side of the system would instantaneously be transferred from compression to tension. The columns along the sides of the structure would either remain in varying degrees of compression or be instantaneously transferred into varying degrees of tension and serve as the fulcrum of the system. If Robertson's theory was correct, the system would stabilize long enough for human beings to escape. We'll see in a moment what happened when Mr. Robertson's theory was put to the test. For now, let's shift gears and talk about fire protection. Primary fire protection was provided by spray-applied insulation such as that shown in the screen and a riser and sprinkler system. This is not a picture of the World Trade Center. This is a common commercial office building that I use to explain to non-engineering audiences what spray-on insulation looks like and what a typical concrete decking system in a commercial office building looks like. This is not what is in place in the towers. Fire compartmentalization was provided by the floor slabs and a double thickness of drywall around 3 sets of emergency stairs in the central core. It's important to remember this slide. In 1993, a terrorist attack struck the tower's underground parking garage. It killed 6 people and created a giant crater in the basement. But those thick, heavy steel columns and the damper system barely felt it. Many of us in the steel industry at that time felt pretty smug about our material and Leslie Robertson's design, probably not unlike the scribes and engineers in Genesis. In July 2001, developer Larry Silverstein, then 70 years old, signed a 99-year lease with the Port Authority of New York and New Jersey to manage and sublease the World Trade Center buildings. Mr. Silverstein had an early doctor's appointment on the morning of September 11th, 2001. He had intended to cancel the appointment and go straight to work at his office in the North Tower. His wife found out, raised the devil, and insisted that he keep his doctor's appointment. While Mr. Silverstein was at his doctor's office, American Flight 11 was being flown south over Midtown Manhattan. It crashed into the north face of the North Tower at 8:46 a.m. United Flight 175 was flown over Staten Island, turned north, and crashed into the south face of the South Tower at 9:02 a.m. Following the impact, those 236 steel columns and the outrigger trusses shuddered and swayed, and then did exactly what Leslie Robertson had designed them to do. Load paths were instantaneously adjusted, compression was transferred into tension, the welds and bolts and dampers and design theory held. And then there was the fire. Each aircraft contained about 10,000 gallons of fuel. The installation was immediately blown off much of the steel in the impact areas. The double thickness of drywall around the central core was, of course, no protection at all. Between 1,000 and 3,000 gallons of fuel were immediately consumed in what is termed as the fireball effect. The remaining fuel spread across the impact floors and down interior shafts, igniting floor fires along the way. When fully engaged, the fires covered 5 acres in each building. Scientists can approximate the energy of fires from their smoke plumes. Analysis of these plumes suggests a peak total rate of fire energy output between 1 and 10 gigawatts. For comparison, a typical single-unit commercial nuclear power plant will have an output in the 1 gigawatt range. This means that the instantaneous energy output from each of these fires approximated the energy output of 10 or more nuclear power stations. I asked the students at this point what young engineer would have predicted this type of stress on the structural system. I always hesitate when I show this slide because if you look closely, you can see occupants of the building looking out through the spaces through the windows they've knocked out above the impact area. And I tell the students that we must always remember that we work for real human beings. What we do impacts the life safety of other human beings. Because of the length of time between impact and collapse, almost everyone below the impact areas was able to evacuate. Tragically, almost everyone within and above the impact areas, human beings, were trapped and unable to evacuate. Remember, all 3 stairs were located in the central core area, encased in drywall, severed and destroyed by the collisions. There was one very lucky exception. Remember also, the towers contained the world's largest electric elevator motors. I use this slide to demonstrate to non-engineering audiences the relative size of those motors and to show the audience the relative size and location of a rotor inside an electric motor. This is a rotor out of one of the World Trade Center elevator motors after the collapse. The mass of those motors in the North Tower was just great enough to buffer the impact just long enough to create a small passageway through which 12 people in the North Tower were able to escape. These were the only survivors above the impact zone in either tower. As temperatures rose, the floor trusses lost rigidity and bowed into what we engineers call catenary action. As the fires grew still hotter, The temperature in those big exterior columns exceeded 2,000 degrees, what we engineers call the modulus of elasticity of the columns was degraded, and their critical buckling strength was exceeded. To explain buckling action to non-engineering audiences at this point, I usually ask the audience to make a T out of their hands, to press down with the hand on the top and let the knuckles in the lower hand bend outward. This is called buckling action. It could have initiated failure in the towers even if the lateral support of the tower truss system had been maintained. When the lateral support was compromised, the columns were doomed. At 9:59 a.m., 56 minutes after it was struck, the south tower collapsed. The north tower continued to stand until 10:29 a.m. when, as we know, it also collapsed. The World Trade Center towers stored more than 3 × 10 to the 12th power joules of potential energy. That's enough potential energy to slingshot a 1,000-pound automobile around the Earth 46 times. Once collapse initiated, this potential energy was rapidly converted into what the engineering students know as kinetic energy. This caused an immediate progressive series of floor failures described as a pancaking effect. I'm going to run through a series of 20 slides now that demonstrate 3 × 10 to the 12th power joules of kinetic energy in action. You'll see first the collapse of the south tower and then the collapse of the north tower. North tower standing, south tower starting to collapse. South tower collapsing. Further and more. At this point, the south tower is essentially collapsed. The north tower is still standing. North tower still standing. North tower begins to collapse. North tower down. The Cold War term nuclear winter has been used to describe the scene in Lower Manhattan after the collapse. 2,982 victims from 90 separate countries died in the attacks. 2,753 in New York City, 184 at the Pentagon, and 45 in Pennsylvania. One of the untold stories of the World Trade Center collapse involves the bathtub. You remember the bathtub. When the debris from the towers crashed down through the bathtub, it demolished the structural members that were providing lateral stability to hold back the Hudson River and hold up the surrounding buildings. After the attack, there was no lateral support for those foundation walls other than the debris itself. The World Trade Center destruction could have been indescribably worse if the bathtub walls had failed. Incredibly brave structural engineers, heroes really, some of them not all that long out of school, literally dove into the darkness of the rubble, devised an ingenious interim fix, and the bathtub walls held. More about one of those heroes in a moment. There was never any question that New York was going to rebuild. Within 7 months, expressions of resolve, similar perhaps to something from Genesis, were being heard again in New York. For example, here's a quote from that time by Paul Goldberger, architectural critic for the New York Times and the New Yorker magazine. Quote, "It is important that New York rebuilds the tallest buildings in America. Something that we had was taken away. We have to show the world that we have the willpower to build it back again. So now let's roll the clock forward. And at this point, I asked the students to imagine that they are young engineers just out of the University of Kentucky College of Engineering, just hired to join the teams of world-renowned architects and engineers like former UK professor Daniel Libeskind or Santiago Calatrava. They and their team are called in before the site has even been fully cleared, and they're asked to design a new World Trade Center where the original had stood. They have a blank canvas. The redesigned World Trade Center's heart is one World Trade Center. Its soul is the September 11th memorial. Every year, at the precise moment of the attack, an uninterrupted wedge of sunlight will strike the memorial. Tower 1 is the tallest structure in the Western Hemisphere, considered a primary target for terrorists and designed as such. The tower tapers and twists from a square base through 8 isosceles triangles, forming a perfect octagon at the midpoint of its height, and then tapers and twists again into a square top, rotated 45 degrees from the base. The taper and twist breaks up the wind, enabling the tower, in theory, to survive a 1,000-year hurricane event. The tower contains enough steel to build 13 Eiffel Towers and enough concrete to fill a string of cement mixers lined up bumper to bumper, stretching 300 miles, roughly the distance from Louisville to Chattanooga. The first 20 stories of the tower are essentially a bunker. The pedestal is engineered to protect the tower from a larger bomb that exploded in 1993. The first 20 floors above grade are encased in both steel and concrete. To avoid the metaphor of a bunker, above ground, the concrete is covered by a glass and aluminum facade. Between the pedestal and the spire, there is a heavily reinforced system of beams and columns, forming another steel tube. An outrigger truss again connects the tube to the core. Horizontal fire compartmentalization is achieved, this time by a floor system built to the standards of a highway bridge deck. And here again, we have, for a non-engineering audience, a picture of a typical commercial office building with a typical concrete floor deck, and a picture of a highway bridge deck, which more closely approximate the current floor decks in one World Trade Center. The core of the tower is encased in heavy concrete rather than drywall. At their base, the core walls are 6 feet thick. At the midpoint, the walls are 4 feet thick, and at the top, they are 2 feet thick. These walls are more typical of the mass concrete in a dam than anything ever seen before in a commercial building. The strength of the concrete in this building exceeds the strength of the concrete in the Hoover Dam, and of course, it's loaded with steel reinforcement. Every great event spawns an epilogue. Leslie Robertson's structural design for the original World Trade Center was the subject of intense scrutiny, including a formal FEMA investigation that was commissioned on September 12, 2001, during a conference call with the Deputy Director of FEMA and the presidents of the American Society of Civil Engineers and the American Institute of Steel Construction. I was privileged to participate in that call as counsel for the American Institute of Steel Construction. Some of the legal counsel involved at that time were not satisfied with the conclusions of the initial FEMA investigation, so there was a later separate investigation commissioned by Congress into the causes of the collapse, this time conducted without any outside assistance of the public. There was also massive litigation alleging building code violations and engineering errors, and lots of disinformation. There were neither building code violations nor engineering errors. It was confirmed by both investigations that Leslie Robertson's design met or exceeded all building code requirements and all professional standards of the day. It's now recognized that had Mr. Robertson applied traditional design theory, the tower would have collapsed immediately upon impact and tens of thousands more lives would have been lost. Leslie Robertson's innovation and his original research literally saved tens of thousands of lives. When I delivered a version of this presentation to a conference of structural engineers in Johannesburg several years ago, they were surprised to learn the facts of the tower design and collapse. And I was surprised to learn that based on news reports they had received in South Africa, they thought that the towers had been destroyed by the CIA. Since 2001, Mr. Robertson has been the recipient of 9 prestigious international design awards. He is clearly the most honored structural engineer in the world. This is a poster that accompanies a 2018 documentary on his life. Since 2001, he has designed a whole generation of striking, innovative structures around the world. Here are a few. More epilogue. Earlene Hatfield has degrees in civil engineering and architecture from the University of Nebraska. She's a friend and colleague, and I use her life story to make a point with the engineering and architecture students who hear this presentation. Immediately after graduation, Earlene went to work for a structural engineering firm in New York City. Earlene was one of the young engineering heroes who dove into the rubble of the World Trade Center collapse and devised an interim fix that saved the bathtub. Earlene spent 6 months at the site every day, forsaking her career to attend to what she and her employer felt to be more important work, protecting life safety. Earlene is now recognized as one of the rising stars of her generation of structural engineers. She was recently the recipient of an International Design Award for her work as the structural engineer of record on the Mercedes-Benz Stadium in Atlanta. And back in the land of Genesis, the land of the Tower of Babel, the monumentality gene is alive and well. The Burj Dubai Tower was opened in 2011 to earn the title of the world's tallest structure, but not for long. Saudi Arabia is currently completing Jeddah Tower. It will reach more than 1,000 meters above the desert floor, almost twice the height of one World Trade Center. And in the waters surrounding the land of Genesis, the USS New York, LPD 21, has been on patrol. The ship's mission is to track down and neutralize terrorists anywhere in the world. The bow of the New York was built with 7.5 tons of steel recycled from the World Trade Center towers. The ship's motto is never forget. And while we do not forget, life goes on. Society continues to express its greatness through its monumental structures. The work of great engineers continues. I'm going to close with a 3-minute video explaining the theory and features that comprise one proposed design for the last of the towers to be built on the World Trade Center site, Tower 2. In this video, the lead architect making the proposal, who is not all that much older than some of the students I talked to, explains his design theory. This may be the first example the students will have seen of commercialization of engineering design. His presentation is full of energy and optimism and monumentality, and I think it's a fitting note on which to end this presentation. Then I'd be happy to take your questions. Let me know if the sound comes through okay on that.
It sounds great, David.
The completion of the World Trade Center will finally restore the majestic skyline of Manhattan and unites the streetscapes of Tribeca with the towers downtown. Tribeca, the home of lofts and roof gardens, meets the glass canvas of skyscrapers. The heritage city blocks of Tribeca meets the vertical towers of the World Trade Center. From Tribeca, it will appear like a vertical village of singular buildings, each tailored to their individual activities, stacked on top of each other, forming parks and plazas in the sky. From the World Trade Center, the individual blocks unite, completing the spiral of towers framing the memorial. Horizontal meets vertical, diversity becomes unity.
Okay, questions?
Great, David. Thank you very much for that fascinating presentation, front to back. So to our attendees, let me remind you that you can ask questions of David through the Q&A function that is available on your Zoom interface, or if you would like to just use the raise your hand function, we will pull you in. You can ask your question orally yourself. While we let people orient themselves, David, let me start the questions and ask what you understand about the terrorists. So did they understand the design of the building thoroughly? Was it lucky that they were able to bring them down, or did they make a study of the structure and formulate their plan around that understanding?
Rudy, I don't know the answer to that. My inclination is that that they did not know and from what I've read, that is more speculation than it is an engineering report. I think they were lucky. But I don't have facts to back that up. And let me add to that a little bit. And I think if you remember toward the end of the presentation, I said that current wisdom is that had traditional design been employed in this, a traditional structure would have collapsed pretty much upon impact. And that may have been what the terrorists were counting on, but I don't know that for sure.
Great, thank you for that. Okay. So Still waiting for some questions to come in. I've got another one for you. And that is, what is the current timeline for Tower 2? Is there one for that last piece?
I do not know the timeline. It's currently still under construction, but I do not know. And I actually have clients involved in that, but that's something I can look into, and I'll get something more precise on that.
Chris, go ahead with your question, please.
Thanks, David. This is Chris Noble. That
Hi,
wonderful
Chris.
talk. I know you can do this well, and you did it again. Question, however many years ago, and you referred to it, some of the counter information by a bunch of structural engineers supposedly was in the form of an hour-long video purporting to support the CIA theory. Has that been totally debunked? And where did it go wrong in terms of its analysis?
I am not certain where it went wrong. In my understanding, Chris, and by the way, Rudy and other participants, Chris is an excellent construction lawyer in Boston who is probably the leading attorney in the country or maybe the world representing design professionals. I do not know where that went wrong, Chris, other than the possibility that people thought that explosives may have been placed in the building, that no one could actually fathom the amount of energy that was created by that fire. Another problem with the fire was that when the central core was taken out, it left chases down through the building. So all of the jet fuel that was not consumed in the initial blast ran down the chases and lit fires along the way, as I said, and it was essentially like lighter fluid in a charcoal grill. And everything caught fire immediately. I think my recollection, now that I'm thinking about it, is that no one could fathom that amount of energy from the aviation fuel that exploded. And I think that's where it came from.
Thank you.
David, we've got a couple of questions that have come in on the Q&A. I'll read those for you. The first one from an anonymous attendee reads, how was the cleanup organized and what things had to be considered during removal of the debris?
That's a tremendous question. That in itself is a tremendous story. A consortium of 6 of the largest construction companies in America volunteered their services to organize the cleanup. And as you know, the cleanup went on for almost a year. The Structural Engineers Association of New York mobilized and kept structural engineers on the site to assist the cleanup crews in the process to make sure it was safe for them to enter a certain area. There are stories about construction workers who, then the fire raged inside the debris for weeks, if not months afterwards. There are stories about how construction workers would stand on these big heavy columns with acetylene torches, cutting it into pieces that could be hauled away until the heat of the columns burned through the bottom of their work boots. There's an account of 12 weeks later, a drag claw uncovered molten aluminum still down in the debris, several scores of feet. The Actors Guild from Broadway set up a food kitchen on the site, and Broadway actors, stars, came down to the site and served free meals to the cleanup crews. It was everything that left the site was examined by both the FBI and by these various investigative teams. one could talk a couple of hours just about the cleanup involved. Everything was taken to a facility on Staten Island by barge from the site. That's sort of the tip of the iceberg of the cleanup.
Great, thank you. Our next question comes from Juan Fitzpatrick, and Juan asks, what was the cost for the rebuilt Tower 1, and what company won the award for construction?
The construction went in several phases. There were several prime contractors. I can't give you all of their names right now. The structural steel, which was the major component of the tower, which is the one I'm most familiar with, was actually awarded to a steel erecting company out of Canada, and the steel for the reconstruction was awarded to a steel fabricator in Montreal. This is probably the most inspected steel construction process in the history of the country. At one point, I knew the exact figure. I believe for the entire site, it's in the range of $16 billion. It's in that general order of magnitude. And let me elaborate on that a little bit, because my memory is coming back to me. There were actually 12 separate prime contracts awarded by the Port Authority of New York and New Jersey in the rebuild, and that very much complicated the reconstruction process, because you have a lot of Indians involved when there are 12 separate prime contractors.
Okay, we've got, there's two closely related questions here. So David, let me ask, I'll state both of them verbatim, but you'll see that they're quite closely connected. So the first is from an anonymous attendee who asks, or who states that David, you stated you got involved on September 12th. How did you get involved, and what was the feeling the day after? So that's the first question. The second comes again from Pete Friedrich. David, did I understand you correctly that a panel in which you participated commenced the day after September 11th? Could you describe the process for that panel?
Yeah. One of my clients at that point before retirement was an organization called the American Institute of Steel Construction that is an engineering research and standard setting body that writes the engineering codes and standards for construction of steel frame buildings and bridges in the United States. The deputy director of FEMA, the president of the American Institute of Steel Construction, and the president of the American Society of Civil Engineers immediately scheduled a conference call to put together the most highly qualified panel of investigators that they could identify to immediately start what they intended to be a non-bias investigation of the original design and the reason for the collapse, because all of these people were business people and they knew there would be questions about this. As general counsel for the American Institute of Steel Construction, I was asked to participate in that conference call, and I did. Most of the facts and figures I related came out of the report from that investigation.
Great, thanks. And we're coming up on the bottom of the hour here. We've got one more question for you, and it's a good one. Comes from Keith Wigginton. Are you aware of Richard Gage's work? And also, World Trade 7 was not hit by a plane, but it did collapse. And so what can you tell us about why that building fell?
I am aware of Richard Gage's work, but I can't recall any specifics. I recall the name, and you'll have to, there was substantial damage to a number of buildings around the site. World Trade Center may have been the building that contained a very large tank full of diesel fuel that was used to power emergency generators. one of the surrounding buildings held that diesel fuel, that reservoir, and it caught fire and demolished the building. I can't remember specifically if that was 7 or not, but there was a great deal of collateral damage. A piece of a jet engine was found on a rooftop 6 blocks away. At least one of the planes went all the way through one of the buildings, or parts of it did. The Deutsche Bank building, which was across the street, had one of those big staggered steel sections sticking in the side of it like a fork in the side of a wedding cake or something. Huge amount of collateral damage, but for the purpose of this presentation, we focused on the towers. But you could do, this could easily be a full semester's course at an engineering school or sociology, you name it.
Great, David, thank you very much for the fascinating presentation and all the insight and the details. It's always a great story, and I've heard it a couple of times, and I always manage to come away learning a few new things, so really appreciate it. So everyone, if you would join me in a round of virtual applause for Mr. David, not Mr. Ratterman, David. Thank you very much. We really appreciate it. And I want to say thank you to the attendees. We appreciate you taking time out to participate in Engineering Anywhere. Keep an eye out in your email for news on our next webinar series. For now, take care. Have a great weekend. Thanks, everybody.